Section 4.1, Vector Spaces and Subspaces. We've worked a bit with vectors, including some ordered pairs and ordered triples and things like that, where we looked at vectors of real numbers. But some of the properties of those vectors of real numbers can be extended to vectors of other mathematical systems. So we want to take that idea and run with it and think about just what is a vector space in general. And basically what it's going to be is a collection of objects that behave the way that vectors in Rn would act. And when we put together such a collection, we're going to call the elements of such a set vectors. A vector space is a non-empty set V of objects called vectors, on which are defined two operations, addition and scalar multiplication, where the scalars are real numbers. And those two operations must satisfy the axioms below. The axioms have to hold for all vectors u, v, and w, and for all scalars c and d. First of all, when you add two vectors u and v, it stays in the vector space. The second axiom says that scalar addition is commutative. The third says that scalar addition is associative. There's an identity element, 0, for vector addition. There are inverses. For each u, there's a negative u, so that when you add them together, you get the identity element 0. Now, in terms of scalar multiplication, when you multiply a vector times a scalar, it stays in the vector space. Scalar multiplication satisfies the distributive property across addition. Scalar multiplication satisfies the distributive property across the addition of the scalars. We also have a type of associativity in axiom 9 that says that when you multiply the scalar CD times the vector u, it's the same as scalar C times the vector d times u. And the last axiom that must be satisfied is that there has to be an identity element for the scalars. And in this case, it's the scalar 1. 1 times vector u is still the vector u. Here's our first example of a vector space. Suppose we were to take the set of 2 by 2 matrices, where the entries of the 2 by 2 matrix are real numbers. This is going to satisfy all 10 axioms necessary for a vector space. For example, when you add two of these vectors, of course they're matrices, but we're thinking of them as entries of a vector space now. When you add these two matrices, you get another 2 by 2 matrix again that belongs to the vector space. When you multiply one of these matrices by a scalar, in the normal way you do scalar multiplication for matrices, it's going to satisfy the axioms of scalar multiplication. And also the matrix addition will be commutative, associative. You'll have a 0 vector that's the all 0 matrix, and to come up with an inverse with respect to addition, not the usual inverse, which is with respect to multiplication, but to come up with an additive inverse, you just take the negative of the matrix. Just take the entries in the matrix and switch the signs, and you'll come up with the inverse of your 2 by 2 matrix with respect to addition. So this is going to satisfy all of those 10 axioms. Here's another example of a vector space. Let n be an integer greater than or equal to 0, and let p sub n be the set of all polynomials of degree at most n. Members of p sub n are going to have the form polynomial p of t equal to a sub 0 plus a sub 1 times t plus a sub 2 times t squared, etc., all the way through the sum of a sub n times t to the n power. So the a sub 0, a sub 1 through a sub n, those are your real number coefficients on your polynomial, and t is a variable that represents a real number. In this context, p sub n is going to be a vector space. It's going to satisfy all the properties of polynomial addition, and it's going to have all the properties of scalar multiplication times these polynomials, and they're going to satisfy the 10 axioms for a vector space. Let's take a look at how a few of these axioms are satisfied. let's define P of t to be this polynomial with coefficients a, and Q of t to be a polynomial of at most degree n with coefficients b. And let's let c be a scalar. For axiom 1, we need to show that when we add two of these polynomials, we get another polynomial that belongs to this same vector space. Well, what happens if you add two polynomials of degree at most n? What happens is you're going to get a new polynomial by adding like terms. So you'll add the constant terms, you'll add the t terms, you'll add the t squared terms, etc., until you finally add the t to the power n terms. And when you add those like terms, you get a new polynomial of degree at most n. And so what's happening is that when you add polynomials of degree at most n, you get another polynomial of degree at most n. So we do have this closure property for polynomial addition, and axiom 1 of the vector space is satisfied. Let's prove axiom 4 that there's a zero element for the polynomials that make up this potential vector space. And to show axiom 4, you have to show that there's an identity element with respect to addition, that there's a 0, and when you add 0 to your vector, you get that vector back again. Well, if we have a polynomial that consists of all 0 terms, terms where every coefficient is 0, then when you go ahead and add the polynomials by adding like terms, you're adding 0 to each degree term, and adding 0 is not going to change the coefficients of the original p. So you get the polynomial p back again, and p plus the vector 0 is going to be p again, and we have axiom 4 being satisfied. Let's jump ahead to axiom 6. Axiom 6 says that when you take a member of your vector space and multiply it by a scalar, you should get a member of your vector space all over again. And so what happens if we take a polynomial p of t and multiply it by scalar c? What do we get? And just by the nature of the polynomial, you have a polynomial with lots of terms. When you multiply it by a scalar, you have to distribute that scalar across each term. And so what we end up with is a new polynomial with coefficients c times a sub 0. C times a sub 1 is going to be the coefficient of the t to the 1 term. And you continue the pattern all the way up to c times a sub n, which is the coefficient of the t to the n term. And since those coefficients are all real numbers again, and since this is a polynomial of degree at most n with coefficients from the real numbers, you're getting another polynomial back again. You're getting another element of p sub n. And since you're getting another element of p sub n all over again, axiom 6 is satisfied. And so what we've done is we've proven 3 out of the 10 axioms. The others are not that hard to prove, and we'll leave them up to you. But what you're going to see then is that this polynomial space, this collection of polynomials that is a vector space, that it satisfies all 10 axioms. One way to make a vector space is to take a subcollection of some larger vector space. When we do that, the smaller nested vector space is called a subspace of the larger vector space. The nice thing about subspaces is that they're easier to verify. Instead of having to prove all 10 axioms, we only have to show that 3 of the properties hold, I should say. And once we can show that those 3 properties hold, the rest of the axioms will fall into place just from the properties of the larger overarching vector space. And so the 3 properties you have to show that your subcollection is indeed a subspace is that, first of all, the 0 vector belongs. You have to show that vector addition is closed. And you have to show that scalar multiplication is closed. If you can show those 2 closure properties plus the 0 vector belong to your subspace, you can actually prove that it is a vector space, that it's not just a subset, but a subspace. So it's a little bit easier to prove. Let's look at some examples. Suppose we were to take the set of vectors. Now these are vectors from R3, but we're a little more specific. We don't just want any old vector from R3. We want to have a vector from R3 of the form A0B, where A and B are real numbers, but the middle component is always 0. Let's show that this is a subspace of R3. Okay, R3 is a vector space. Let's show that this is a smaller vector space nested within R3. So we have to show three things. We have to show the 0 element belongs, and we have to show both closure properties. Okay, first of all, does the 0 element belong? Well, yes, because if I take the vector with components 0, 0, and 0, it's an element of H. So all we have to do is let A be equal to 0 and let B be equal to 0. And we have the 0 element belonging to H. So that's not too bad. Now we're supposed to show that we have the closure property. Well, what happens if I add two vectors from H? If I take two vectors in R3 that have a middle component of 0, when I add them together, the sum also has a middle component of 0. And therefore, adding two vectors from H gets me another vector from H. Lastly, to show that the third property holds here, what happens if I take a vector from H and multiply it by a scalar? Well, when I multiply the vector times the scalar, it's going to multiply each component by the scalar. And that'll give me, components for the first and third component. But when I multiply the middle component, which was 0, times a scalar, 0 times a scalar is still 0. So the middle component will still be 0. We will have, in fact, a vector from H. And so scalar multiplication of the vectors of H is closed. We proved all three axioms. And so, this is a subspace of R3. Here is a picture of that subspace. If you were to think about R3, R3 is a three-dimensional space. And so you can, picture the entirety of three-dimensional space here. That's the original vector space. What's the subspace? Well, the subspace is the subspace of points that have a 0 second coordinate. And so it's essentially going to be the plane that has axes x sub 1 and x sub 3. So you can have any first component, you can have any third component, but the second component has to be a 0. And that puts you in this subplane of the larger vector space. So the entire vector space is three-dimensional space, but the subspace is this two-dimensional subset of that larger space. Okay, well, let's try another example and see if it is a subspace. Suppose I were to take all vectors of the form x plus 1. So we have a vector here with two components. So if it's going to be a subspace and its components are real numbers, then it's going to be a subspace of R2 because there are two components. So is this a subspace of R2? Now you can see that we have this interdependence between the first and second components. What we're saying is that the second component is equal to the first component, add 1. Is this really going to be a subspace of R2? And the answer is no. One problem that we have right off the bat that shows that this is not a subspace is that it doesn't contain the 0 vector. If I make the first component 0, then the second component is 1. If I make the second component 0, then the first component is negative 1. There's no way to simultaneously make both components 0, and so the 0 vector can't belong to H, which we can also see from the picture. Since this is not going through the origin, it's not going to be a subspace. So that's one way to show that this isn't a subspace. Here's another way to show that H is not a subspace of R2. One of the things that's supposed to happen is that when you take two elements of H, when you add them together, you should get another element of H. But working out a quick, simple example shows that that's not typically going to work. If I add vector u and vector v, with the selections being made u equals 0, 1, v equal to 1, 2, then when you add them together, you get a vector u plus v, that's the vector 0 plus 1 for the first component, 1 plus 2 for the second component, and so we end up with the vector 1, 3, and that is not in H because the second component is 2 added to the first component. And so that's another reason that this is not a subspace. And here's a picture of that. What happens if this were really a subspace, then when you add 2 vectors from your subspace, you should get a third vector from your subspace, and that's not the case. You can see here that when we add the vectors associated to the points on this line, you get a third point that's not on this line. And so property B of vector spaces, or property B of subspaces, is failing, and so this is not a vector space. Here's a shortcut for determining subspaces. If V1s, V2, etc., all the way through Vp are vectors belonging to vector space V, then the span of that collection of vectors is a subspace. So what we're saying is that if you just take some vectors and look at their span, you automatically get a subspace. All right, well, let's try to check this out. To show that it's a subspace, we're going to have to show that the three properties of subspaces hold. We have to show that we have the zero element belonging plus the two closure properties. So first of all, does the zero element belong? And the answer is yes. The way to show that the zero vector is in the span is to just take a zero multiple of each of the vectors v1 through vp. Because when you're taking the span of v1 through vp, you're just saying that that's the set of all vectors. That's a linear combination of v1 through vp, and one particular linear combination is to just take all zero scalar multiples. When you do that, you'll get a zero vector. So 0 does belong. We also have to show that we have our two types of closure. So let's work to that end. Let's start with the additive closure. If I take two vectors from the span and add them together, do I get another vector from the span? And the answer is yes. If we look at u and v, where u is equal to a sub 1 v sub 1 plus a sub 2 v sub 2, etc., all the way through a sub p v sub p, and if v is the vector b sub 1 v sub 1 plus b sub 2 v sub 2, etc., all the way through the sum b sub p v sub p, then when I add them together, I can add like terms. Add the v sub 1 terms, add the v sub 2 terms, add the v sub p terms. And when we do that in each case, you'll be adding an a term to a b term. And according to the properties of vector spaces, you can use the distributive property to factor out v sub 1, and factor out v sub 2, and factor out v sub p. And when we do that, what we have is you have a sub 1 plus b sub 1 as the coefficient on v sub 1. You have a sub 2 plus b sub 2 as the coefficient on v sub 2. And you have coefficients for each vector that are real numbers. And so what we have is just a linear combination of v1 through vp, which means that this is an element from the span. But if it's an element from the span, then we have this closure under addition. Okay, so to finish showing that the span of any set of vectors is going to be a subspace, we need to show that it's closed under scalar multiplication. So take a vector v from the span, and we can use the definition of v that we just used on the previous slide. When we multiply it times scalar c, I can go back to the definition of v as an element in the span, and then I can use the distributivity of scalar multiplication to distribute across that sum that defines v. And when we do that, we'll get cb1 as the coefficient of v1, CB2 as the coefficient of V2, etc., all the way through the last sum end, which will be CBP times V sub P. And what this tells us is that this is a linear combination of V sub 1 through V sub P. That you're taking scalar multiples of V1 and V2 and all the vectors through V sub P and adding them together. So, CV is in the span. We can now say that this is closed under scalar multiplication, and since we've shown the three properties of subspaces hold, we can say that this is a subspace. So, to recap on that theorem, what we were saying now is that if you take some vectors from a vector space and take their span, that span is going to be a subspace and therefore a vector space in its own right. So to recap here, to show that something is a subspace, you have to show that the three properties apply, or show that it's the span of some set of vectors. To show that something is not a subspace, you just have to identify which of the three properties does not hold. Let's look at one more example here. Suppose we have the collection V, which is a set of vectors from R2, where the components are of the form A plus 2B and 2A minus 3B, where A and B are real numbers. Is this a subspace of R2? Why is it a subspace, or why is it not a subspace? Let's determine why. Okay, so let's start by writing the vectors. Instead of an ordered pair form, let's write them in the column form, and let's split it along the lines of the addition and subtraction. So let's write it as the vector A2A plus the vector 2B negative 3B. And we've split it up in such a way that the components in that first vector have a common factor of A. The components in the second vector have a common factor of B. Let's factor out the A and the B. So that original vector is A times the vector 1, 2, plus B times the vector 2, negative 3, where A and B are acting like scalar multiples. But we're done now, because if we let V1 be the vector 1, 2, and we let V2 be the vector 2, negative 3, then what we're saying is that this collection V is the span over those two vectors, V sub 1 and V sub 2. Okay, let me say that one more time. If V sub 1 is the vector 1, 2, and V sub 2 is the vector 2, negative 3, then this collection of vectors is the span over those two vectors. And anytime you look at a span is going to be a subspace. So we do have a subspace, and it's a subspace of R2, using the theorem that we just proved about spans. Anytime you have a span, it's a vector space. It's a subspace. Here is another example. Suppose we have the collection H, which is a subcollection of vectors from R3, where the vectors are of the form A plus 2B for the first component, A plus 1 for the second component, and A for the third component. Is this a subspace of R3? And the answer is no, it's not, because there's no way to get the zero vector. Again, looking at the second and third components here, A plus 1 and A, they can't simultaneously be 0. If A plus 1 is 0, then A isn't. If A is 0, then A plus 1 isn't. So there's no way to get a zero vector here, and if you don't have a zero vector, you don't have a vector space. You don't have a subspace, and therefore you don't have a vector space. So property A of subspaces fails, and so this is not a subspace. Earlier we had an example that said that the collection of all 2 by 2 matrices was a vector space. Here we have a subcollection of matrices of that form. We want to know if that subcollection is a subspace or not. And so to be a subspace, we should either show that the three axioms hold, or show that it's a span. And so let's split it up. Let's separate the A components of each term and the B components of each term, and then factor out the A and the B. But when we do that, what we're saying is that each vector in this subcollection is in the span of two vectors, where the two vectors are the matrix 2, 0, 3, 0 and the matrix 0, 1, 1, 3. Since H is a subcollection of vectors in that span, H has to be a subspace, because anytime you have a span, you have a subspace.